Welcome to the deep dive. This is where we take that pile of sources you've got, research notes, papers, maybe a study guide, and really unpack it.
Yeah, we cut through the noise, get straight to the core ideas, and figure out what it all means for you.
And today, we're diving into something pretty cutting edge, a new AI agent. It's called Code Researcher.
And its job, tackling bugs, but not just any bugs.
Right, we're talking about the really complex ones, the kind you find deep inside massive software systems. Think the Linux kernel, that kind of scale.
It's a great topic because, honestly, fixing bugs in that kind of systems code, it's a whole different ballgame than your typical app debugging.
Totally different. And the current AI coding tools are getting good, but they often, well, they struggle here.
They really do.
So our mission today is to figure out how Code Researcher actually tries to do this. We'll focus on the innovations, the technical bits from your sources that show why it might be a big step forward.
Okay, sounds good. Let's start with the why. Why is this so hard? Your sources really hammer this point. Home systems code is just challenging.
Yeah, things like operating systems, network drivers.
The low-level stuff, it talks directly to the hardware.
And the scale alone is mind-boggling. You mentioned the Linux kernel example from the sources.
Yeah, something like 75,000 files.
And 28 million lines of code. Imagine trying to find one tiny bug in all that.
It's vast. And it's not just big, it's dense. Technically dense?
How so?
Well, it's often C, C++, so I'm dealing with things like raw memory pointers, bit-level operations, loads of compile-time macros. It's very intricate stuff. Performance is key, so the code gets complex.
Okay, so dense code. What else?
Interactions. Bugs often pop up because of how different parts of the system interact, maybe in subtle ways. Concurrency problems, memory management across modules. It's not always just one function that's broken.
A change over here could break something way over there.
Exactly. And then there's the history.
Ah, right. These systems weren't built yesterday.
Decades of changes, hundreds, maybe thousands of developers over time. Sometimes you can't understand why code is the way it is without digging into that history. Why was this change made 5 years ago?
That context is crucial. And for AI, there's another big hurdle, isn't there? The input.
Yes, this is critical. Often when these systems crash, all you get is a stack trace.
Which is just a list of functions.
Pretty much. A list of function calls leading up to the crash. It's super ambiguous. It doesn't have a nice, clear, human-written, here's the problem description that, a lot of current AI tools kind of rely on.
So the AI has to start from this very cryptic clue.
Right. It needs a different approach.
So let's connect this back. Why should you, our listener, care about fixing bugs in, say, the Linux kernel?
Well, because this stuff runs everything. Your phone, the cloud server storing your data, network infrastructure. Its reliability is fundamental. Finding and fixing these bugs efficiently matters a lot.
Okay, so that sets the stage. Enter Code Researcher. And your sources use this specific phrase for it. Not just a coding agent, but
a deep research agent for code.
Deep research. That sounds significant. How's it different from, say, other agents like SWE-agent mentioned in the sources?
Well, agents like SWE-agent often do well on benchmarks, like SWE-bench, right? But those benchmarks typically have human-written issues, often for smaller code bases.
Issues that might give hints like, check this file or look at this function.
Exactly. They're often designed to follow those hints, find the likely files, and make edits relatively quickly. Code Researcher is built for the opposite scenario.
The ambiguous stack trace, the massive code base.
Precisely. It's designed for multi-step reasoning and, crucially, deep context gathering. It has to actively find the relevant information itself.
Okay, and the sources break down its process into, what, 3 main phases?
Yeah, conceptually. Phase 1 is analysis. This is the core deep research part, understanding the crash.
Okay, analysis first, then
Synthesis. Taking what it learned and actually generating a code patch, a fix.
Makes sense. And finally,
validation. Testing that patch. Does it actually fix the crash without breaking something else? Super important.
Let's really dig into that analysis phase then, because that seems to be where the core innovation lies, this deep research idea. How does it work?
So the agent has a toolkit, basically, a set of actions it can use to explore the code base and its history.
What kinds of actions?
Some are fairly standard, like search definition, find where a function or a data structure is actually defined, or search code. Use patterns like regular expressions to find where a function is called or where a variable gets a certain value, things like that.
Useful, but maybe not revolutionary on their own. What's the special sauce?
The big one highlighted in your sources is search commits.
Ah, commits. So the history again.
Exactly. This action lets the agent search through past commit messages and the actual code changes associated with them across the entire project history.
Wow. So it can automatically ask questions like, when was this function last changed? Or are there any past bug fixes related to this variable?
Pretty much. It's about understanding the evolution of the code. Your sources point out this historical search is a key differentiator from other agents discussed. It links directly back to that challenge of understanding decades of changes.
Okay, so those are the actions. It's tools for looking around. But how does it decide what to look for? How does it reason?
That's where the reasoning strategies come in. Think of them as guiding principles, powered by the underlying large language model, that help the agent interpret the info it gathers and decide the next best step.
And one strategy uses that commit search, right?
Absolutely. A key one is causal analysis over historic commits. Your sources emphasize this is vital for those subtle bugs introduced maybe years ago.
How does that work?
Instead of just looking at the code now, it actively traces the history. It looks for related changes over time. When was this line added? Why? Did a previous change nearby introduce a problem, like that memory leak example in the sources?
Tell me about that.
Yeah, the agent used this strategy to trace back through commits to find where memory was allocated. But the corresponding deallocation, the freeing of memory, was missing from a related change much earlier. That historical link was the key.
So it's like detective work across time.
Kind of, yeah. And this specific historical reasoning seems unique to code researcher among the agents compared.
What other strategies does it use?
Well, there's chasing control and data flow chains. Basically, following the path of execution, what function calls what and how data gets passed around to understand the sequence leading to the crash.
Okay, tracing the program steps.
Right. And also, searching patterns and anti-patterns. This draws on classic software engineering ideas. Look for common ways things are done correctly, patterns, and look for deviations, anti-patterns, that often signal bugs, like maybe forgetting to check if a pointer is null before using it.
Got it. So it's exploring, using these actions, guided by these reasoning strategies. That must generate a lot of information. Snippets from different files, commit messages. How does it keep track?
Good question. That's the job of the structured context memory. It's like the agent's notepad.
Okay.
Every action it takes, every result it gets, it's all recorded there. And crucially, at each step before deciding what to do next, the agent reviews this memory.
Ah, so it builds up a picture over time.
Exactly. It pieces together context from potentially many different places, files, history, and uses that consolidated understanding to guide the next step of its research.
So it's very iterative. Explore, learn, add to memory, decide next exploration step based on the bigger picture.
Precisely. It has to be iterative. Given the ambiguity of the start and the sheer size of the search space, it can't just guess the answer in one shot.
Okay, that analysis phase sounds quite sophisticated. Then, once it thinks it understands the bug, we move to synthesis and validation. We can probably cover these a bit quicker.
Sure. Synthesis is basically take the relevant clues gathered in the analysis phase, filter them down, form a hypothesis about the bug, and then ask the LLM to generate a code patch to fix it.
Propose the actual code change.
Right. And then validation is critical. Apply the patch, rebuild the system,
Compile everything.
and run the exact same script or steps that caused the original crash.
Does it still crash?
If not, great, patch successful. If it still crashes or if something else breaks, then the patch failed. This empirical check is non-negotiable for these complex systems.
Makes total sense. Okay, so theory sounds good, innovative approach. How did it actually do in tests? What did the numbers show?
Your sources focus on a benchmark called kBenchSyz, which sound like it's built for this exact problem.
How so?
It uses real Linux kernel crashes, 279 of them, found by a tool called syscaller.
Syscaller. That's a fuzzer, isn't it? Throws random inputs to find bugs.
Exactly, a kernel fuzzer. And the bugs it finds often just come with that ambiguous stack trace. So kBenchSyz is a realistic, tough testbed.
Okay, the proving ground and the results.
The key number is crash resolution rate, CRR. Code researcher hit 58% CRR on kBenchSyz.
58%. How does that stack up?
The comparison point, SWE-agent, achieved 37.5% on the same benchmark using the same evaluation setup.
Whoa, okay, 58 versus 37.5. That's a pretty big jump.
It really is, nearly 20 percentage points better. And the sources connect this directly back to that deep research capability.
Oh.
They measured how many files each agent typically looked at during a debugging attempt. Code researcher explored an average of 10 files per trajectory.
Okay, 10 files and SWE-agent.
Only 1.33 files on average.
Wow, big difference.
Huge. It clearly shows code researcher digging much deeper and wider into the code base, which seems necessary for these kinds of bugs. It's not just staying in one or two hinted files.
So the performance gain seems directly linked to its ability to conduct that broader research.
That's the argument, yes. And the context it found also overlapped better with what human developers looked at when they fixed the same bugs, about 64% overlap versus 54% for SWE-agent. Suggests its research is more relevant too.
And this was measured using pass at 10. What does that mean?
Right, pass at 10 means the agent got up to 10 attempts to solve each bug. And each attempt had a budget, like a maximum of 15 calls to the language model to keep things comparable.
Got it. Is this just a Linux kernel thing, or does this approach work elsewhere?
Seems more general. They tested it on 10 crashes from FFmpeg.
Ah, the multimedia library. Different domain.
Yeah, complex codebase, but different. And Code Researcher fixed 7 out of the 10 FFmpeg crashes with just minor tweaks. So the core ideas seem transferable.
Okay, impressive results on a tough problem.
Yeah.
But it's not magic, right?
Mm.
What are the limitations mentioned?
Definitely not magic yet. A big one is inherent to the LLM's used context length.
The amount of text the model can consider at once.
Exactly. Even the state-of-the-art models mentioned, like Gemini 2.5 Pro, might handle, say, 100,000 lines of code max in their window.
But the kernel is 28 million lines.
Right. You just can't feed the whole thing in. The iterative search helps, but it's still a constraint. The model never sees the entire system at once.
And even with the text that is in the window, LLMs can struggle.
Yeah, there's that lost in the middle problem.
Yeah.
Information buried deep inside a very long input prompt sometimes doesn't get used as effectively by the model.
So if you pull context from 5 different files and stick it all together for the LLM,
it might struggle to connect the dots perfectly if the key pieces are in the middle. It's an ongoing challenge for large context models.
what about the fixes themselves? Are they always good, clean patches?
The qualitative analysis in your sources is really interesting here. They looked at the types of patches Code Researcher generated.
Okay. What did they find?
Well, sometimes they were accurate. Basically, the same kind of fix a human developer would write. Correct. Addresses the root cause. They gave an example for a JFS file system bug.
Good. What else?
Sometimes over-specialized. The patch fixes the crash, but maybe adds extra checks or logging that isn't strictly needed. It works, but it's a bit much, like adding extra logging in a Bluetooth driver fix example.
Okay. Functional, but maybe not elegant.
Then incomplete. The agent finds the right area, understands part of the problem, but the patch doesn't fix all instances or misses some edge cases. Useful insight, but not a full fix, like a concurrency bug fix that only patched one function.
Almost there, but not quite.
And finally, incorrect. The patch just fails validation, doesn't fix the bug, or maybe even breaks something else, often because the initial diagnosis was wrong. They had an example where it misinterpreted an integer issue in networking code.
So, a real mix. It shows that while it's powerful, you absolutely need that validation step. You can't just trust the generated code blindly.
Absolutely not. It shows it's a powerful assistant for research and patch generation, but human oversight and rigorous testing are still essential. It's not fully autonomous yet.
Okay, so let's wrap this up. What's the big picture here? Code Researcher seems like a significant step, moving AI coding into tougher territory.
I think so. It's tackling these really hard, ambiguous bugs in huge, critical systems code bases, something that was largely out of reach before.
And the key seems to be that deep research approach in the analysis phase.
Yeah, that multi-step process, using actions like search commits to look at history, using specific reasoning strategies like that causal analysis over commits, and keeping track with that structured memory. It all allows it to go way beyond just editing files suggested by a human.
It's actively investigating, exploring the code and its history to find the real problem.
Exactly. It shows AI starting to perform genuine, deep investigative work within these complex software artifacts.
Which is a vital step if we want AI to help maintain the foundational software everything else relies on.
Definitely.
So here's a final thought for you, the listener, to chew on. We've seen how Code Researcher performs deep research by exploring code, tracing execution, analyzing history to debug complex systems. Where else could this kind of AI-driven deep research be applied? What other fields involve wading through vast amounts of complex information, reasoning over time and changes, and trying to find the root cause of problems? What might this signal for the future of software development? Sure, but maybe also scientific discovery, historical analysis, or other knowledge-intensive work.